Thank you. Go ahead.
Copy that. Good afternoon, everybody. As mentioned, Joel Payne. I lead the mechanical engineering group over here at Keck. Wanted to bring you, at the recommendation of Andre Aguez, a talk that has been both shortened and updated. I gave it SPIE last year talking about peer repair. So a whole bunch of people involved with this, all the co-authors down there, several folks, not Keck folks, actually, which we'll talk about here in just a second. So, as some starting background, um, the Keck 1 telescope effectively functions like an air hockey table upside down. We are injecting oil into each one of our feet, the hydrostatic bearings here. That oil floods over the side of our journal into a gutter system, is pumped back through, and it is actually floating on oil. Now, we've had a problem for quite a while now, of a little bit of oil seepage getting past the gutters, getting places where it is not supposed to be. So you can see the dark kind of stain here on the side of the concrete, or in some areas when we cut away the oil, we actually had legitimately standing oil here. This is a problem because the construction of our pier, this is again our main primary load path, is a reinforced concrete wall with a layer of cementitious grout. Cementitious grout, it's a lot like concrete, but it doesn't have the aggregate rock. Well, this layer of grout here, kind of in between the main journal and the concrete pier wall, is slowly breaking down. And that means it's getting softer. We are starting to see deflections. With too much deflection, you could effectively beach the telescope and have it immobilized because we don't float high enough to account for those changes in slope. So the failure mechanism here is a bit like hydraulic fracking. When you have oil that's getting places that it's not supposed to be, the pressure as it comes by both is, purging out the sides, kind of an erosion mechanism, and then any teeny tiny cracks in that concrete is forcing them wider. There have been a variety of attempts at repair. The first noises were actually heard on the Keck 1 telescope, I believe, in 2001. This was an epoxy injection that was done in 2007. This was a 2018, a like for like repair of cementitious grout. But this picture is actually fairly infamous because the substrate that we were digging out underneath that grout was so soft that you could actually brush it away with a wire brush there. Um, so I'm skipping some information on history here, but this is a deterioration that has been kind of a slow march. We see this coming, we're tracking it, but notably, it changes our pointing. So we can compensate for the amount of pointing and deflection we have. It's harder to compensate for changing deflections. So this chart is the deflection as you spin around looking at any one individual foot. And the blue data is from 2020, and then the red is from 2023. So the deflections are downward, hence you're seeing that we very distinctly do have growth there over time. Some areas that look like they were quite fine suddenly we're growing in deflection notably. So clearly this is something we needed to do something about. Thankfully, we did a trial repair. I'll be telling you about in a moment here. That we're able to take one bad area and say, hey, we're going to make this better. And by doing that, we've now marched into production repairs, which is one of them is happening right now. So if you prefer your data color coded, you can just see the difference, red and yellow, height and deflections. Again, 2020 on the left, 2023 on the right. How much change we're seeing in that couple of 3-year kind of window we're looking at. Now, somewhere along the line, thankfully, we ran into across some cohorts over at JPL. This is one of their 70-meter antennas that speaks to spacecraft like Voyager. And they had had a great deal of success switching from a cementitious grout to an epoxy grout. So a two-part plastic that is effectively oil impervious. When looking at grout, there's a whole lot of things you care about that I don't have time to talk about, but suffice it to say we were looking at. Um, we did a whole bunch of material qualification testing. So this was a surrogate of our journal where we've got anchor bolts, you've got a plexiglass top, and you effectively have to pour from the side, and you want kind of a nice, smooth, almost moving like lava type flow that goes over the top, throughout that void underneath the journal. We also proved that we very much needed to use heat. So this is the visitor gallery on summit. So we're testing at altitude, but using heat to see how this epoxy would cure. Because once we turn on the air conditioning, we'll probably never get back to a cure temperature inside that dome. So, as noted, lots of material testing. So strength, we looked at creep, we looked at bearing surface, doing some Photoshop to figure out how much bearing surface we had, but really worked out a process that we thought was going to go quite well. We needed to prove how we could heat up the pier to have a cavity that was warm enough. We effectively needed 85 degrees for 72 hours. This was the first time I ever personally shut down the telescope. I've gotten to be forced to be a little bit more comfortable with that in the time since. But we were able to hit our heating target, so that worked pretty well. Quite a bit of figuring out how to do this. So this device over here on the left is a really glorified C-clamp that grabs onto the journal and then can support a drill stand. We're core drilling to pull this out. There's also a challenge with our oil gutters, that first picture I showed you, in terms of how you would traditionally pour something like this. This was JPL, where they pour and they end up with kind of a block protruding out the side. That wasn't going to work for us. We needed to have that kind of geometry maintained. So I will take credit for the crazy idea of using a curved waxed guillotine to break off a chunk of grout when we were done. But really, my engineers get the credit for making the crazy idea real and able to be able to profile the edge of what we were pouring there underneath. So this is kind of one of our final tests. We're now using much thicker plexiglass to actually have some stiffness like a journal, looking at two different depths of pour in case we need to carve down deeper. Again, we want to get down to a good substrate. That was part of the goal here. And you can see kind of that beautiful lava looking flow that I was talking about there. So we're into 3 rounds of repair now. The first one was a trial repair. We did this little baby section of about 16 degrees here, and this was now 10 nights off sky. But just to walk through the process of what's involved here, it starts out with core drilling. This is the real version of some of the CAD I was showing you a moment before. We carve Olympic rings into the side of this, avoiding our anchor bolts. Then we go in with chipping hammers and we carve out those the scallops that are left from the rings to end up with a flatter surface. Step 3 is a scabbler, which is a pneumatic tool with carbide tipped fingers that's really good at finding cracks and voids and kind of imperfections that want to chip themselves loose. So this is much more what the surface, what we want it to look like before we're getting set up to pour. We did set up heat blankets on this to make sure that the cavity we were pouring into was also at a good temperature. Came back the next morning, and lo and behold, we actually have oil weeping our way up out of the concrete below. So we used a hammer sounding test to go through and find if you could hear the thunk, you knew something was loose instead of kind of a sharp noise. So although the picture on the right isn't nearly as beautiful and consistent, this is actually down to good substrate. And that's something we really, really wanted to be confident in this process. The molds are pretty complicated. We use profile gauges to be able to align things to rough surfaces. We're wrapping foam around our anchor bolts just in case we ever do need to go redo something. There's thermocouples down inside the cavity. And then as noted, here's the reality of that kind of curved bisecting steel piece I was talking about. We call it the curved guillotine. Um, so mix and pour requires lots of respirator protocols. We all had to go get trained up and figure out particular cartridges and whatnot. Visitor gallery is quite toasty at this point. We have it holding it at about 85, 90 degrees with the air conditioning blocked off in order to maintain that temperature that we're looking for. I know I'm going too fast to let folks read charts, but you can trust me that we did in fact achieve the 85 degrees for 72 hours that we were hoping for. And thankfully, trial repair, this was kind of the first repair that has been done in 20 years of attempts at this point through various different people that have come through, that this data stayed stable as we were going along. So we do still have some fast growing areas. So with the trial repair in hand, we then this March started an actual production repair. So this was effectively 7 times what we did as a trial repair. We had 81 staff on summit between contractors, alternates, our staff, just a lot of logistics making this happen. We were working 7 days a week. I did all the layouts of kind of who needed to be where, but we were actually able to finish ahead of schedule. You did a little bit more time cleaning to make sure things finished up and did the project on budget, which I'm very, very proud of. So production repair had some differences. We had to pull off the actual oil tray instead of just working in one high spot on the far side. So this was the old oil tray removal. We got a little bit more clever in terms of using our core drills instead of chipping in between things. We're now actually coring at an angle in between anchor bolts as well to be as efficient as we can. We know time off sky is a very big deal. Doing a little bit more in terms of dust mitigation and cleaning, tenting things as we're going. This is actually, we refined this even a little bit further since we've shown you this. If you want to see what it looks like now, or what it will look like when we're all done, much more like the picture on the left-hand side. So we have a brand new modular oil tray system. We can now unbolt this if we ever need to go after something. The beautiful curved surfaces I was talking about, and the oil is now forced off into particular spots. So how did it go? That's the question. This is all results now from downtime one. Blue data was the 2023, green data is current. Peer repair, we still have, sorry, at the portal, we still have some increased deflections.
Sorry to interrupt. We're running out of time.
Understood. I'm on my last two. Uh, we did have fantastic results in the biggest and worst areas that we're going after. These were kind of all the areas in gray were the things that we did before. We are starting to see just a hair of something where we did the trial repair, but we're tracking that, and likely is because we didn't really stop the oil before we got into production. So these are some areas we deferred. I can't promise we're done with this next one. This is what we're all doing in downtime two, which is happening right now. So there is some split teams up there. I'd be up there with them, except I was just solving a big shutter issue. Thankfully, we have returning contractors to lean on, and that was truly a lightning presentation. So thank you very much.
Hi, everyone.